Hello, everyone. Thank you for coming along today to I guess this is our first academic event of the year, I think. I don't know, everything's a blur at the moment. Hopefully everything's working on Zoom. It looks like it's good on our end. So today we have a talk from the lovely, luscious Flynn Linton, a close personal friend of all of us. Some would dare say a hero, a god among men, even, and he's going to be talking to us about the double copy relations, subtitled A Small Man's Take on Quantum Field Theory, Gravity, and Black Magic. So it should be quite interesting. Merry Christmas. Thank you.
All right, yeah, so today I'm going to be talking about double copy relations, which is a pretty interesting little piece of physics. And basically, in short, it's a little mathematical link between particular quantum field theories and gravity. And you'll note that I mentioned like two key things here that we'll get into a little bit more detail shortly. The first is quantum field theories and also gravity. So before we get started, can I have a show of hands? Who's done second year quantum? No, you haven't, Alex. Keep your hand up if you've done or are doing third year quantum. All right, not many. That's okay. Yeah, so today I'll be talking a little bit about what exactly quantum field theory is, what gravity is, and how these two things can be related to each other via the double copy relations. So quantum field theory is a bit of a pain in the ass. It's really hard, but it's our like most complete theory that tells us how particles behave with other particles and interact with each other. And we use fields to describe this, as I'm sure you could gauge from the name quantum field theory. So here we've got two examples of what fields are. The one at the bottom is called a vector field, which is generated due to the electrical charge of a positive and a negative point charge that we have there, creating a dipole. And at each point in space, we can assign a value, and that value in this case is the strength of the electric field. So it's something that we can measure. And in the top example, we've got like a temperature gradient of the ocean on the Earth. So this is a scalar field, and every single point mapped out across the ocean has a particular value that we can measure, and that value in this case is the temperature. So in quantum field theory, fields are a little bit more complicated. Instead of just existing in regular 2- or 3-dimensional space, they exist over 4-dimensional space-time. So that's 3 spatial dimensions, one so we're familiar with, and also 1 temporal dimension to describe the evolution of the field through time. And when we excite these fields, that's how we describe particles. So an electron field, for example, if we excite the electron field, we get an electron. And same with other fundamental particles as well. So if we were to summarize quantum field theory in a sentence, it'd be a way to describe the dynamics and interactions of quantum fields, as opposed to classical fields. So quantum fields are discretized rather than continuous media. So mathematically, all of this comes down to, well, in quantum field theory at least, Lagrangian formalism. So the Lagrangian, which I'll explain what that is in detail in just a minute, describes the dynamics and interactions of the particles within our field theory. So we know the Lagrangian by this funky looking L, and we can use that Lagrangian to evaluate something called the Euler-Lagrange equations, which is like a generalized form of the equations of motion of a system, which describe its dynamics and evolution through time. And then we get the equations of motion. So for example, something that most people are somewhat familiar with in everyday life, quantum electrodynamics, which is maybe not too familiar. But it's the quantum analog of classical electrodynamics, which describes classical electromagnetism, which describes how electric fields and magnetic fields interact with one another, and that the electromagnetic force is mediated by photons, light. So in quantum electrodynamics, this is what the Lagrangian looks like. The first term there is the fermion coupling term, and so that tells us about the interactions between photons and matter particles. And the second term there is the electromagnetic interaction, which describes how photons can interact with each other. And this funky looking F thing here is called the electromagnetic field tensor. And that basically describes, well, it describes the 4 potential A of the field, which tells us that how the field behaves basically. And so if we plug this Lagrangian into the Euler-Lagrange equations, we get this nice compact form of Maxwell's equations, which will describe the dynamics and evolution of electromagnetic fields through space and time. So we can extend this a little bit further to obtain what we call the standard model. You've probably all heard of it in some way or another, but it's basically a combination of a bunch of different quantum field theories, and it's a gauge theory. It satisfies these particular symmetries. All of these things are just different types of rotations through space and time. And the standard model predicts quite well 3 out of the 4 fundamental forces of nature that we know of. The strong nuclear force, which tells us how quarks, which make up protons and neutrons and also some other particles, interact with one another. The weak nuclear force, which acts on a nuclear and atomic scale, and also the electromagnetic force, which we saw a little bit before. So yes, gravity is a very naughty force. We've not yet able to quantize it to the point where we can actually make predictions and measure them. At the moment, classical Einstein gravity, so general relativity, is our best theory of gravity that we can measure, and it works quite well. And it describes how space-time, 4-dimensional space-time, curves when we have massive objects inside of it. So flat space-time with no massive objects is described by special relativity, and then when we add mass, we obtain general classical Einstein's relativity, which is general relativity. And unfortunately, gravity isn't perfect. It does break down at certain points in space-time, like black holes and the very start of the universe. So the Einstein field equations, which are kind of like gravity's analog of its equations of motion, kind of break when we're dealing with these sort of singularities. So there have been a number of attempts at creating a theory of quantum gravity. I'm only going to talk about one of these today because only one of them is really relevant and I don't understand the other 2. But M theory or string theory and loop quantum gravity, I'm not going to be talking about those today, but I will be talking about quantum field theory in a curved space-time, which is a semi-classical theory and is probably the simplest quantum gravity theory that you could produce. And all of these theories predict the particle, the graviton, as the mediator of the gravitational force, which hasn't been discovered. It's a purely mathematical object that we've created to try to make our theories work. And QFT in curved spacetime is a perturbative theory. So this thing here, G mu nu, that's what we call the metric, and that describes the curvature of spacetime. So the first term in that expression, eta mu nu, describes flat spacetime. So what spacetime looks like when we don't have any masses. And then that kappa thing is, you can think of it as like a coupling constant that tells us how strong the gravitational field is due to a mass. And that's proportional to Newton's gravitational constant, which we see in classical physics. And the h mu nu is the new bit, the perturbative bit, which describes what happens to space-time when we introduce masses. And so this h term satisfies the wave equation. So we know that graviton solutions must satisfy the wave equation. And that's directly from Einstein's field equations, which is a classical theory, which is why this is a semi-classical theory, because it still draws on some components of classical Einstein gravity, except we're kind of forcing it into a quantum realm doing this. So here's an example of something that we can calculate in quantum field theory. It's called a scattering amplitude. And it basically describes the probability, it describes the final result of this particular interaction as a probability. And so this is a 3-gluon scattering amplitude, which means we have 3 gluons, which are mediators of the strong nuclear force, which is described by quantum chromodynamics, or QCD. And this is what the scattering amplitude actually looks like for 3 gluons interacting with one another. So it's quite simple. There's only 6 terms in this expression. When we try to compute a similar scattering amplitude for 3 graviton particles interacting with one another, we get something incredibly complex, and that looks nothing like what we did when we were dealing with just a 3-gluon scattering amplitude. And so this is a fairly compact form of the scattering amplitude, and it actually has a total of 171 terms. So it's a lot more mathematically complicated. Plus, it's also super difficult to actually evaluate. Well, I don't think you'd be doing this analytically unless you hate yourself. But computationally, it's much more demanding than it is to calculate amplitudes in quantum field theory. And that's using the typical Lagrangian formalism that I talked about earlier to obtain the equations of motion and then determine the scattering amplitudes. Now, I did promise some black magic, and this is the part of the talk where I'm going to talk about the black magic. So buckle yourselves in. All right, the double copy relations. Pretty obscure little thing. I hinted at before, this allows us to calculate particular quantities in our quantum gravity theories using quantum field theory. In particular, one of the main thing that people are focusing on right now is calculating gravity scattering amplitudes using quantum field theory scattering amplitudes. And basically, the double copy works. We calculate a scattering amplitude in Yang-Mills theory, which is, you can think of as like a subset of quantum chromodynamics, which just describes how gluons, the mediator of the strong force, interact with one another. We apply these funky double copy relations, and it spits out a scattering amplitude in our quantum gravity theory. So this is just a little bit of a summary of how the double copy relations work. So just to reiterate on things that I said before. So the scattering amplitudes in quantum field theory are generally much easier to compute than they are in gravity theories. And our scattering amplitudes depend on a number of quantities. Something called the color charge of the gluons. It's what we call a conserved quantity, kind of a analog to how electrical charge is a conserved quantity in quantum electrodynamics. Also, the momentum and polarization of the gluon particles themselves, as well as the strong coupling constant, which describes the strength of the strong interaction. In gravity, the amplitudes depend on, again, the momentum and polarization of our graviton particles that we've created. but also the gravitational coupling, which remember is proportional to just Newton's gravitational constant. So this is what a scattering amplitude in Yang-Mills theory and our gravity theory looks like using the double copy relations. So to obtain the gravity scattering amplitude, we do two things. We replace the Yang-Mills, so the gluon interaction coupling constant, with gravitational coupling, which is this kappa term proportional to Newton's gravitational constant. And we also replace the color charge term, which is kind of like a quantum chromodynamics analog to the electric charge in electrodynamics. And we replace that one with a kinematic factor, which describes like its momentum and things like that. So this is probably best understood by going through an example. It's quite a cool example because we can actually obtain solutions for different sort of objects in classical gravity other than just scattering amplitudes using these double copy relations. And in this example, we're actually going to go backwards. So we're going to start with a solution that we know that we've obtained via Einstein's field equations using classical gravity. And then we're going to invert the double copy relations to obtain something in our gauge theory. So something that's relevant to Yang-Mills theory. So we're going to be dealing with a Schwarzschild black hole, which is the simplest form of black hole that you can construct. Basically, it has no charge and no angular momentum, so it's not spinning or anything. It's completely static in space. Regular black holes aren't like this. They're usually spilling out shit left, right, and center and rotating and moving and things like that. So it's a really idealized black hole, the simplest type you can construct mathematically. And it's kind of like, it's basically a point-like singularity. So if you think back to electromagnetism, a single electron is like, you can treat it as a point charge and it emits an electric field. Similarly, we can think of a Schwarzschild black hole. The singularity is an infinitesimal point of mass, which generates the gravitational field around it. So this is what the Schwarzschild metric looks like, describing the curvature of space-time through all of space when we have a single Schwarzschild black hole in it. So the first term in that expression there, eta mu nu, describes flat space-time when we have no mass in there at all. And the second term, the 2gm on R times this k term here, describes the curvature of space-time due to the Schwarzschild black hole being present. And so yeah, this is what our graviton solution looks like. So the perturbative gravity term due to the black hole. And you can see it's proportional to our coupling constant kappa. So to apply our single copy, it's called the single copy relations. It's the inverse of the double copy relations. As we saw before, first thing we need to do, replace the coupling constant. So we take the gravitational coupling constant, this kappa over 2 term, and we replace it with the strong force coupling constant, G. And then the next step, we replace the mass, which, as I said before, is equivalent to a point charge in general relativity, with the Yang-Mills color charge term. And what we get is quite an obscure thing. We actually obtain the vector potential for a point color charge from the graviton solution. So basically, we've started off with what is essentially a point charge in general relativity. We've applied the inverse double copy relations, and we've ended up with a point charge in our gauge theory. So you can see this kind of unusual duality between our gravity theory that we've constructed and this gauge theory. And yeah, just note it's not actually electric charge. You can think of it as an analog to electric charge. It's a conserved quantity in this particular theory, like the electric charge is a conserved quantity generated by a point charge in electromagnetism. So summarize double copy theory. The Yang-Mills scattering amplitudes, we can use the double copy relations to directly obtain scattering amplitudes in our quantum gravity theory, our semi-classical gravity theory. And this drastically simplifies calculations of gravity scattering amplitudes because they're very difficult to calculate because they're extremely different to our scattering amplitudes in quantum field theory. And Yang-Mills is much, much easier to compute computationally. So we save an enormous amount of resources. It allows us to compute much more complex graviton interactions than we could without these double copy relations. And there's also a bunch of unusual dualities between specific solutions in general relativity and also in Yang-Mills gauge theory. And we saw that example before, the duality between a point charge mass, a Schwarzschild black hole, and a color point charge. And this also actually generalizes to higher dimensions and also is actually valid for some supersymmetric extensions of Yang-Mills theory. So I thought I would end with some open questions that are currently in the field. So first of all, nobody really knows where the double copy relations came from. It was only really proposed, I think it was 2008. So not that long ago. We haven't known about it for very long. And we're not sure if it's evidence of a deeper underlying relationship between gauge theories and gravity or just some mathematical trick just by coincidence. Another question is, are all gravity and supergravity theories, not just this one particular one that we've looked at, double copies of any gauge theory? It doesn't specifically have to be Yang-Mills. Can it be any other gauge theory like quantum electrodynamics or QCD as a whole? We don't know. And something that I read that I thought was kind of interesting is that perhaps we could use, when we understand these a little bit better, use these outside of physics, outside of astrophysics and theoretical physics in other fields where this duality pops up. But I don't believe there are any situations where that does occur, not just yet at least. That's everything I've got prepared for today. Does anybody have any questions? Oh, it's something that I am hoping to. This isn't actually my area of research. I did research in computational atomic physics. This is something that I'm hopefully looking to do as part of my PhD, and I thought it was pretty interesting. So read some papers on it. Oh, yeah, kind of looking out for supervisors. Thought this kind of thing sounded pretty interesting. Yeah.
I know you said you don't actually know the answer to this question, but if it wasn't just like a mathematical coincidence and there was sort of a relation like the underlying theory, what would you expect like that would mean?
I'm not sure, but if there was some underlying relation between gravity and gauge theory, like at this stage we know that gravity is much more complicated than gauge theory is, as we saw like this scattering amplitudes that we compute in our semi-classical quantum gravity theory are extraordinarily complicated compared to regular quantum field theory. So I don't know, it would give us a little bit of insight on how those two things are related and maybe why gravity does not fit in like we want it to, why there's so many problems. Perhaps it could answer why gravity is so much weaker than all of the other three fundamental forces. So if I just go back a bit, yeah. The other three fundamental forces of nature, the strong nuclear force, the weak nuclear force, and electromagnetism, are like orders of magnitude greater in strength than gravitational force. So I think it's something like 10 to the minus 30 or something times smaller than these other forces. So it's like a non-negligible difference. It's extraordinarily weak compared to the other forces. And it just happens so that it doesn't fit into the standard model for whatever reason. So I don't know, hopefully it could answer questions like that. Gauge theory just means that our quantum field theory satisfies, well, sorry, our Lagrangian satisfies particular symmetries. So we can rotate it in particular ways. Where did oh, actually it was that slide. The standard model, for example, satisfies this symmetry. I don't remember off the top of my head what exactly each of those rotations are. Jesse might, I don't know. Yeah, I know U1 is electromagnetism. SU3, I think, is this QCD. Yeah, because electromagnetism and the weak nuclear force combine together into electroweak theory. And the strong nuclear force is not, the strong nuclear force is pretty complicated because you've got the gluon interactions between quarks that make up like protons and neutrons and mesons, I think, which are just two quarks. But you've also got the residual strong force. I'm not very familiar with that at all. That acts on a nuclear scale, I think, as well. Like, which one is most promising, or like what would the implications be of finding a theory where it somewhat is unified? Oh, if you can't unify them. Look, I'm no expert on any of these things, any of these candidates for quantum gravity. I haven't actually studied in detail any of them, so I couldn't really answer that question. I don't know anything about string theory or loop quantum gravity. I don't know, they've been working on string theory for like, what, 60 years? Probably longer than that. Hasn't really had any major breakthroughs since like the construction of M theory. I don't know. Which one's my favorite? Well, I haven't studied the first two, and I've read a little bit about the third one. The third one is intuitively very easy to understand because it's just like, it's not necessarily you're doing perturbation theory, but it's perturbative corrections, whether that's strong perturbative corrections where you can't use perturbation theory, or small perturbative corrections where you can use perturbation theory, like low energy gravitational waves, things like that. You can obtain graviton solutions of those, which are just plane waves, I think, using that. Yeah. So the question was, if the double copy relations, if double copy theory could be used outside of specifically astrophysics and theoretical physics, where potentially might it be used? I know that like condensed matter physics has a lot of, I haven't studied the condensed matter physics in very much detail at all, but I know condensed matter physics does have a lot of relevance to symmetries, kind of like that we use in quantum field theory. So I suppose that perhaps it may be relevant in condensed matter physics. I really don't know. It was more of a footnote on a paper more than anything. I don't think anyone's really thought of that in great detail because we don't understand it enough to begin with. Yeah. What was that? Will I be thinking about it? I don't know. I don't really remember exactly what I would be doing in a PhD because I kind of blanked that a couple of months out of my memory because it was very stressful. Yeah. All right. That's it, I guess.
Yeah, okay. Yeah, thanks for giving that talk, Flynn. Hopefully everyone found that really interesting, and hopefully people on Zoom, you had a good talk, had a good time too listening to that. So yeah, can we just give Flynn like another round of applause? He deserves it. He's a trooper.